Okay, so what I want to do here is look at further graphs. So these are graphs that are not some of the typical graphs we've seen earlier in the chapter or in our study of maths, and want to see how a lot of the techniques that we've been using will be needed in order to find out what these graphs actually look like. So starting with our first example here, let's try and find out what the intercepts might be for a function of this nature. In fact, the first thing that would be good to know is, are there any values of x that we're not allowed to have? And in our case, the values of x we can't have will be any value of x that would make the denominator equal to 0. And in this case, there are no values of x that would ever make this denominator equal to 0, because if x is a negative number, when you square it, it'll become a positive number. So this denominator will always be equal, it will never be equal to 0. And we may actually have some functions where there's a square root sign. And as far as this level of mathematics is concerned, we can never have a negative value inside the square root sign, but we don't have that to deal with for any of these examples here. So we'll continue on. So there are no values of x that we're not allowed to have in this one. Next step then will be to see whether there are any intercepts on the x and y axes. So let's put a little heading there of intercepts, and we'll first address the x-intercept. And for the x-intercept, you should know that y will have to equal 0. So if I make y equal 0 in this expression, 0 equals 1 on x squared plus 1. You know, there is no value of x that we can put into this expression that will make that expression, this part, equal to 0. There are no values of x that will make that the case. And so that means there is no x-intercept. It doesn't intercept with the x-axis at all. So let's check out the y-axis, the y-intercept. And that means that we'll have to make x equal to 0. And in this case, y will equal 1 over 0 squared plus 1, which equals 1. So there is actually a y-intercept at y equals 1. Okay, there's a y-intercept at the coordinates of 0, 1. So we'll actually just jot that down. The coordinates here will be 0, 1, that's the y-intercept. Alright, so there's no values of x that we can't have, and then there are no intercepts on the x-axis, and there's an intercept for the y-axis. Now the other thing that would be quite helpful for us to figure out is what happens to this function as x gets extremely large. So the limit as x approaches infinity. So let's check out what happens with that. The limit as x approaches infinity of 1 on x squared plus 1, what we can see is that as x becomes very, very large, x squared becomes much, much larger, and 1 on an extremely large number is very small. So the limit of this function will actually be 0. So as x becomes very large, it will become 0. It'll be a slightly positive thing. It'll be, if we look at this as we approach infinity, positive infinity, as we go along the x-axis in the positive direction out to infinity, this whole number in the bottom will be 1 plus a very large number. So it'll make this whole thing very small, and we'll be approaching the x-axis from above the x-axis. If I put a little set of axes here to try and give an indication of what this might look like when we sketch it, we might extend that x-axis in both directions. So here's our x-axis, here's our y-axis. As I said before, we know that this is going to have a y-intercept at 0, 1. It goes like that's going to cross right there. We know that as we go a long way out towards the direction of x, where x becomes infinitely large, it's going to move a long way out here, and it'll come down closer and closer and closer to the x-axis, but it will never quite reach the x-axis. So the x-axis is asymptotic to the curve. Now what would happen though when we go in the negative direction, the limit as x approaches minus infinity of 1 on x squared plus 1, well actually the same kind of thing's going to happen, is because even though it's a negative x, all these values on this side are negative values of x, but when we square them, they're going to become positive, because negative squared is a positive. So really what's going to happen is we're going to have a similar thing occurring out this side, where the curve will have the x-axis as an asymptote. Now as we look at this, the curve will actually, I haven't really drawn this very accurately, but it'll have a little lump right here as it comes through to the y-axis. It'll have a little lump here, and then it'll peter out. And if you look at that, that actually looks like it could be symmetrical about, well, my curve doesn't look like it's symmetrical. Crumbs. Here we go. I'll try and make it look more symmetrical. Maybe that's a bit of an improvement on the symmetry of the curve. It looks like it's symmetrical around the y-axis, and if something is symmetrical around the y-axis, if it's got a reflection symmetry about the y-axis, then it should be an even function. Let's just check to see whether this is an even function. Just do that down here. If I've got function f of x is equal to 1 on x squared plus 1, that's what function f of x is equal to. Let's try it. What's function f of minus x? Well, that would be 1 on minus x squared plus 1, which equals 1 on x squared plus 1, which actually equals function f of x, and that is the condition that we need for an even function, that function f of minus x is equal to function f of x. So this function is in fact an even function. It does have mirror symmetry about the y-axis. It's got the x-axis is asymptotic to the curve, or the curve is asymptotic to the x-axis. That is part of the process.